Section 4.5 Summary of Curve Sketching. So what we're actually going to do in this section is kind of put everything we learned so far in this course to use it into this section to help us sketch a given function, if it's rational or irrational, using all the stuff that we learned so far, from derivatives to asymptotes, intercepts, domain, all this stuff, concavity. We're going to put it together to help us sketch a graph for a function by hand. So what are the things that we're going to be using the whole time? We're going to be using find intercepts. They don't have to be in this order. Asymptotes, derivatives. From derivatives, I'm going to come up with what we call table of variation. Table of variation will tell us when is the graph is increasing, decreasing, all that stuff. It will help a lot in graphing. And then we can find concavity if we would like to use it, if possible, and if it helps. Then we have something I call it particular points. Sometimes you get to the point like, oh, should the graph go up this way or that way? So it helps for the path of the graph. And then put all this together to sketch the graph. So these are the things that we're going to be using to graph any function. So let's look at an example, see how we apply them. How do we sketch the graph for this function, y equals, call it f of x squared over x minus 1. When it comes to intercepts, what do we have in the intercepts? When x is 0, y is 0. X 0, y 0. So we have 1.00. That's the graph's gonna go through it. So this point's consider both x and y intercept at the same time. So that's the first thing to do. Next thing is asymptotes. How do you find the asymptotes here? First thing is the denominator. If I set the denominator equals 0, I get x equals positive 1. That's a vertical asymptote. And if you remember, the degree of the top is bigger than or equal. Actually, if it's bigger than the denominator, the degree of the top bigger than the bottom. So what do we have? The degree of the top is bigger than the degree of the bottom. So we have what we call oblique asymptote, oblique or slant asymptote. How do we obtain that? To obtain it, we use long division. We divide the top by the bottom. X squared divided by x minus 1. What do we have? X squared minus x. Switch these signs and add. Bring the x down. I can still move on with this. X minus 1, multiply or switch the signs and add. That's the remainder. Whatever you get on the top, that's gonna be the slant asymptote, x plus 1. I'm gonna call it SA, slant asymptote. So we got two asymptotes. Asymptote is the line that the graph is gonna approach, but hopefully it will never touch or cross the vertical, but it could be in very special cases or very special functions or very little functions the graph would cross or touch the slant asymptote. Not all the time, in only very few cases. Now we need to find the derivatives. The derivative of the function is, we're going to take y equals x squared over x minus 1. To find the derivative of this function, we use quotient rule. The denominator square, denominator times the derivative of the top, minus derivative of the denominator times the numerator. So by the quotient rule. So now this stays the same. This is 2x minus this is 1 times x squared over x minus 1 squared. If you simplify it here, you get 2x squared minus 2x minus x squared divided by x minus 1 squared. What do we get? Y prime is x squared minus 2x divided by x minus 1 squared. We can factor x on the top, x minus 2, all divided by x minus 1 squared. That's the derivative for the function. Now what we need to do is, after the derivative, we're going to create what we call table of variation. Table of variation. This table is very important. So what are we going to put on the table? Let's check that out. We have always x, y prime, and then we're going to have the y. X, y prime, and y. What goes on the x part? So what goes on the x part are the critical numbers, and what makes the denominator 0. So basically VAs, vertical asymptotes. So the critical numbers here we have, if we set that equal to 0, we're going to get on the top equal to 0, then that gives me x equals 0, x equals 2. So 0 and 2, 0 here and 2 there. Remember this, the domain of this from negative infinity to infinity, and 1 here except 1, so 1 was the vertical asymptote. How do we handle this? How did I find this 0 here? This x was 0 when the derivative was 0. And same thing with the 2. Okay? It's a vertical asymptote here. So what I'm going to do, I'm going to put just like kind of like a ladder, let's say. It's like this. X cannot be 1, y prime cannot be, it's not defined at that point. And now we're going to look at, we have 1, 2, 3, 4 regions. Let's see what happens. If I pick a testing point here to find the sign of the derivative, say 3, if you put 3 into this, that's going to give us positive. If you pick like 1.5, that will be negative. If you pick 1/2, that will also be negative. If you pick, let's say, -1, that would be negative times negative positive. Now, when x is 0, what is the y value, the corresponding y value? So if I go back to the original function and substitute x 0, y would be 0. So see what I'm doing? I'm finding the value of y. That's why we substitute x equals 0 into the original function, and x equals 2 into the original function. That would give me 2 squared 4 over 2 minus 1, 1. So that's a 4. Okay, so what happens here? At the plus sign tells me the graph is increasing. This is decreasing, decreasing and increasing. Now what happens at these infinities? Those infinities, below the infinity, there's always a horizontal asymptote or slant asymptote. In our case, it was a slant asymptote. It was y equals x plus 1. Y equals x plus 1. That's the slant asymptote. That's the table of variation. If you are able to get to this point, then the graph becomes very easy to sketch. So now let's see how we graph the function. Let's see how to graph it. So we have x, y. We got x equals 1 as a vertical asymptote. So that's a vertical line, x equals 1. We got y equals x plus 1, x0, y1. -1. Remember, the graph is going to go through the origin, so I'm going to put a big dot there. And what else we have? So from the first one, the intercepts 0, 0, we use that. We use the asymptotes. From the derivative, it helped me to construct the table. And now let's trace this. The graph starts here on the left, near x plus 1, y equals x plus 1. It goes through 0, 0, and then down near x equals 1. So it's going to go near x plus 1, through 0, 0, and down near x equals 1. That's the first branch. Then the next part of the table, it says, it came up from where the vertical asymptote is, went through a point 2, 4. So that's 2. 1, 2, 3, 4. went through this point, and then near y equals x plus 1. Don't forget the arrows. You see, that's the graph of the function. So the derivatives help us to better get a graph. Notice something, I graphed it with no using like what I call particular points. I didn't need any points in this case. But that shows me how powerful calculus is to help us to figure out where is the function increasing, where is it decreasing. Putting all that together about derivatives helps me to sketch the graph by hand, no calculators. We're going to look at another example now. So let's say sketch the graph for y equals x over x squared minus 1. Of course, some people like to find the domain sometimes. So they say, can I just factor the denominator and find the domain? Domain is all real numbers except -1 and 1. So domain, if you like to state that down, is all real numbers except -1 and 1. So -1, 1. That's the interval notation for it. So all real numbers except -1 and 1. Intercepts, we need to find when x is 0, y is 0. So that gives me 0, 0 as both the x and the y intercept. For asymptotes, what we get for asymptotes, we always set the denominator equals 0 to give me the x minus 1 times x plus 1 equals 0, to get x equals 1 and x equals -1 as vertical asymptotes. So we have two vertical asymptotes. And what else we have? The degree of the top x is less than the bottom. Automatically means y equals 0 always is a horizontal asymptote. Note that this can be found when x goes to plus or minus infinity. If you like to see that out, how this happens, if we pass the limit as x approaches plus or minus infinity for the function, what we get infinity or infinity. We can use L'Hopital's rule. And so if you use L'Hopital's rule, that will give us 1 over 2x, which actually goes to 0. So y equals 0 is a horizontal asymptote. After this, we find the derivative of the function. Derivative of the function. Y equals x over x squared minus 1. We use quotient rule again. The denominator will be squared. You get x squared minus 1, x derivative times x. What do we get? Y prime x squared minus 1 times 1 minus 2x times x. X squared minus 1 minus 2x squared over x squared minus 1 squared. We need to simplify to the least. The last step we can do, this is negative x squared minus 1 over x squared minus 1 squared. Notice these two are totally different, the top and the bottom, they're not the same. Don't cancel them. But we can factor a negative out from the top. That gives me x squared plus 1 squared. And this stays the same. Notice something here. Notice something about this. This quantity here is always positive for all x. This is always positive for all x. And there is a negative in the front. There is a negative. So this tells me this whole thing is always less than 0 for all x in the domain. No matter what x is, this will give you a negative value. Since y prime is always less than 0, let's see what happened to the table of variation, or how that's going to look like on the table of variation. This is the table of variation. We get x, y prime, and y. than what we have. First thing, we put the negative infinity to infinity here. As you notice from the domain, we don't have any critical values, but we have -1 and 1, both are vertical asymptotes. So at the vertical asymptotes, we always draw this that looks like a ladder, means it's restrictive. And remember, y prime, the sign of y prime is negative all the time. That tells us that the graph is always going to be decreasing. On the left side, below the negative infinity, it was the horizontal asymptote y equals 0, and here the same way. So this is telling us the graph is going to come near y equals 0, is going to go next down to next -1, x equals -1. Same thing is going to come from near x equals -1 down to x equals 1, and same thing near x equals 1 down to y equals 0. If we would like to sketch the graph to see how this is going to look like, we get x equals -1 is the vertical asymptote. That's one of them. The other one, x equals 1, is another vertical asymptote. So you get -1 and 1. We have y equals 0 is a horizontal asymptote, so sometimes I just write it like this. This is saying it's going to come near y equals 0 to x equals -1. So the only way to do that is to come this way, down this way. And you can take x equals -2 just to test it and see what you get. If you take x equals -2, you're going to get this point. Remember, it's going to go through 0, 0 as a intercept. So now it's going to come from here next to x equals -1 down to x equals 1. So it's going to come this way, down this way. Then the next one is going to come from x equals 1 down near y equals 0. So this is the graph of the function. Note something, just as addition note. The graph, or the above graph, concaves up over which interval concaves up? From -1 to 0, union 1 to infinity. And down means concaves down from -infinity to -1, union 0 to 1. Union 0 to 1. This is those are good to know for this function. How about if they ask us to sketch a graph for a different function? For the function y equals, call it f of x over the square root of x squared minus 1. Notice there's radicals involved here. It makes it more tricky. So what's the first thing? As I said, some people like to find the domain. So let's find the domain. Domain, how do you find the domain? The denominator inside the radical cannot be 0 or negative. So then you get x minus 1, x plus 1 by factoring bigger than 0. And how do I solve this inequality? What I do, I just put that on the number line, -1 and 1. Infinity, negative infinity. Then what we do, we select testing points, we call them. We select testing points. And we can take x equals 2, let's say, x equals 2. And substitute it in here. That will give us positive. If we take x equals 0 here, that will give us negative. X equals -2. That will give us positive. So then the domain, when is it positive? Domain is -infinity to -1, union 1 to infinity. That's the domain. Note something here. This 0, the number 0 is not included in there. So if you happen to substitute x equals 0 into the original function, you will get or anything between -1 and 1, you will get a negative value. And we do not want that to be there. Okay, that's important. For intercepts, if you like to set x equals 0, remember x cannot be 0 because you're gonna get a negative value. You're gonna get 0 over a negative something, like -1. That's not gonna work. It's not a real number. If you set y 0, what's gonna happen? For y 0, you take the top equals 0, so that means if you cross multiply like that, x times 1 is x equals 0. But remember, we said x cannot be 0, so there's none. There's no intercepts. There's no intercepts. What about asymptotes? Asymptotes. What are the asymptotes? The asymptotes, to find the vertical asymptotes, we set the denominator equal to 0. If you square both sides, you get this equals 0. So then x minus 1, x plus 1 equals to 0. So we get two asymptotes, x equals 1 and x equals -1 are the vertical asymptotes. Vertical asymptotes. Now, after the asymptote, this asymptote, what's going to happen? We don't know if there's a horizontal asymptote or a slant asymptote. To do so, what we need to find is basically the limit as x approaches plus or minus infinity for the given function. And let's see if you remember how we did the limits at infinity. One way to do this is to factor x squared in the denominator. So we factor x squared here. That will leave 1 minus 1 over x squared. And then this equals limit as x approaches plus or minus infinity. We take the x squared outside as an absolute value, like so, and that will leave the rest inside. Now notice the limit has two things. One time goes to positive infinity. When it goes to positive infinity, then when you drop the absolute value, you drop it like so, it's a positive. Or it can go to negative infinity. In this case, when you drop the absolute value, put a minus sign. You put the minus sign. So what happens here? This will go to 0, this cancels this, that will leave 1 over 1, 1. This goes to 0, this cancels this, 1 over -1, -1. So this tells us y equals 1 and y equals -1 are horizontal asymptotes. I'm going to write HAs, horizontal asymptotes. So these are the asymptotes. Now derivatives. So now how do you find derivatives? X over the square root of x squared minus 1. So we need to find the derivative of this function. There are many ways to differentiate such a function. We can use the quotient rule if you like, or we can rewrite it. I've seen people doing this, so they bring it up as -1/2 and do product rule. So if you're going to do product rule, it's the derivative of the first one times the second one plus the first one times the derivative of the second one, -1/2 x squared minus 1 to -3/2 times 2x. Then y prime equals 1 over, we can bring this down like so. We don't like to work with negative exponents. Minus, these cancel out, x squared over x squared minus 1 to the 3/2. And then what we do here, multiply by x squared minus 1, x squared minus 1. To get the least common denominator to match here, the x squared minus 1 to the 3/2. So let's see what we get on the top. The denominator is simply x squared minus 1 to the 3/2. On the top we get, this is the first power, not derivative. So x squared minus 1 minus x squared. So then these cancel out, and that gives us y prime equals -1 over x squared minus 1 to the 3/2. That's the derivative of the function. Now what's going to happen here in this is that will help us for the table of variation. Table of variation we call it. So what we get from the table here, the three things we start: x, y prime, and y. Domain from -infinity to infinity. We had two vertical asymptotes, -1 and 1, no critical numbers. So we're gonna put two vertical ladders like this. And let's see what we started with. We started with the domain of the function was negative infinity to negative 1 and 1 to infinity. Negative 1 to negative infinity to 1. And so this means between these two, nothing is going to happen between the asymptotes. And for these two, if you pick, let's say 2, x equals 2, put it in the y prime. That will give you 4 minus 1. That's a positive, and negative there, so that's a negative. That's going to go down. And the same thing for the other one. If you take a negative sign here, that's also going to be negative, so that's going to go down. For the other one is what happened when x goes to positive infinity. When x went to positive infinity, we got y equals 1 as a horizontal asymptote. Y equals 1 horizontal asymptote. For negative infinity, y equals negative 1 as a horizontal asymptote. So now we are ready to graph it, or to sketch the graph for this function. X, y, x equals negative 1 vertical asymptote. X equals 1 is the vertical asymptote, other vertical asymptote. So now y equals negative 1 and y equals 1. So we have y equals 1 and y equals negative 1. So there's negative 1 and 1. It says it comes from y equals negative 1, it goes down to x equals negative 1. So how that's going to go? Negative 1, that's y equals negative 1. Down to x equals negative 1. It's going to come from x equals 1 to y equals 1, like that. That's the other one. These are the two. In the middle, nothing happens. And that would be the graph of this function. So this requires some practice. I would recommend going over the examples in the textbook. Go over these first. Follow the procedure, the steps of that would help you to graph a lot of functions by hand using calculus. Not just pick random points and plot on the graph as we did in like algebra or pre-calculus. And then after that, you would need to go over the examples in the textbook, then attempt the homework problems.